Speaker this afternoon is Luc Nguyen from Princeton, who will talk to us on radial hedgehogs in the Landau-de Gennes model of liquid crystals.
Thank you. I'd like to thank the organizer for the opportunity to participate in this wonderful program, and also the opportunity to give this talk.
Microphone working?
I think it's working. Hello? Maybe I move it closer. Its screen light is on. So. Yeah, is it working or no? Yeah. Okay. Okay. So most of this talk will be joint work with Luc Nguyen, Valery Slastikov, and Agir Zanescu. So let me start by reminding you what the energy functional that I would look at is that I would have a kinetic term, which I will assume to be just pure gradient, and a bulk density term. Now, in top of it, I have this little L constant, which is supposed to be small in my analysis. And this bulk density is a function of the Q tensor, and of course, the Q tensor take value into the space of real 3x3 symmetric traceless matrices. This bulk potential is assumed to be invariant under rotation of the matrix, and so then by linear algebra we know that f has to be a symmetric function of the eigenfunction, the eigenvalue of the vector q. So then that means that it is a function of the trace of q, the trace of q squared, and then the determinant of q. And here we assume that it's traceless, so it's just a function of q squared and trace of q cubic. And throughout the talk, I will assume that it takes this quartic form, even though if I have time, I'll talk a little bit about the case where I truncate it as fixed order, which is a little bit more analytically more challenging. Okay, so the question that I'm interested is to study the behavior of the minimizer of this energy functional as L is going to 0. Okay. So L is about the size of the core of the liquid crystal. So in some physical literature, it's called the vanishing core limit, and I prefer to call it the Austen-Frank limit, and we see why in a minute. Okay. So the expectation of what would happen is that in the limit, Q would take value onto the set where the bulk density is minimized, and this set here can be completely characterized. Can be written as a constant that depends on the constant a squared, b squared, and c squared, and multiplied by a matrix. And this is a uniaxial matrix where this vector n is in the sphere. So now if we replace n by minus n, nothing is changed. So this is invariant under the antipodal map. So this is a projective sphere, and it's an embedded projective sphere in the space of the Q tensor. Okay. Now, regarding the energy, what Q would want to do in the limit is that it would want to minimize just the kinetic part. The bulk is being minimized as constant there, so there's no contribution. So it's just the kinetic part. So then Q is an S star value harmonic map. Okay. So now, if we can say that Q is coming from a vector n, then the vector n here would minimize this gradient of n squared term. So this is the Austen-Frank theory. So what we see is that in the limit, it would want to go to the Austen-Frank theory. Okay. So this has been made rigorous by a work by John Ball and Agir Zanescu, and the answer is that the passage from this one to this one can only be possible if the domain that we look at is simply connected, and that coming from the fact that the target is not oriented. Okay. So in this talk here, I will assume that our domain is a ball or the whole space, so we won't have that problem. Now, there's an analogous model which is a little bit simpler. Is that so instead of looking at Q tensor, one look at a vector, a complex value function, and so this has 2 degrees of freedom, and then instead of the L, we replace it by epsilon square for some other reason. And the bulk potential take this 4th order polynomial in this one here. Now in this case here, the limit manifold would be when this is minimized, so that is a circle. So this is the standard double work potential, and so the limit manifold is a circle. And what we can do in this case is that we split V into the mod the modulus, and then the phase. Now, if we do this decomposition, then the Euler-Lagrange equation for this one split in this form. So now the equation for the phase is awfully nice. It's divergent free, some like elliptic, and then V is always close to 1. So this is a very nice elliptic equation. So in a sense, in studying the limit, the second equation plays no role. Right? You can whatever that you want to get. So then the key thing is just to understand the equation of the modulus. Okay. So now in this simplified setting, you reduce a system, right? So here it has 2 degrees of freedom. Here you have only 1 degree of freedom, more or less. So in this awfully simple case, I wouldn't really say that the study of this equation is simple because it doesn't have. I mean, some of the sign is wrong. However, the reduction from a system to a scalar helps a lot with the study of this one. So now, in our case, we see that the limit manifold is the projective sphere, so it has dimension 2, and then the space of the Q tensor is a vector space of 5 dimensions, so the codimension is 3. Okay. So now, if we take this equation of the Q tensor, we project it onto the limit manifold, or we project it in the transverse direction. In each one of them, we end up with a system instead of a scalar equation. So the reduction that we had before doesn't seem to work in this case. Now on top of that, there is some new feature that come in, is that if we look close to the core, or equivalently if we rescale and make the core of size 1, and the domain is going to infinite, then we're looking at entire solution, then the entire solution are expected to have axial symmetry rather than radial symmetry. And this was not the case in Gimbel's-Landau theory. And this offers some interesting feature from the fundamental difference between Landau-de Gennes and Austin-Frank from this point of view. Okay, so nevertheless, try to give an impression. Is that so the first starting work that was on this direction is by Apala, Mazumdar, and Zanescu, is that the minimizer would convert in H1 to a limit minimizer, and then furthermore, away from the singularity of this limit minimizer, the conversion is uniform. So now Q star is a harmonic map in essence, it's a harmonic map into a sphere. Right? So then singularity of a harmonic map into the sphere is well understood. It's just a bunch of isolated points. Okay. So now from a point of, if one want to study defects in liquid crystal, then the point singularity of Q star is correspond to point defects in Austin-Frank theory. Okay. So what this theory is saying is that, okay, to a certain extent, when L is small, then the minimizer QL is being approximated by this Q star. So in particular, if we have some knowledge about this Q star, we can recover the point defects of QL. Okay. Now, in Landau-de Gennes theory, besides point defects, we also have line defects and wall defects. And the question is, okay, say that for some reason I know this Q star, I already know about the point defects of QL, can I say something about the line and the wall defects? So that's my starting point in this one. So then, so this is about the time I got to Oxford, and then I talked to Argyll Zanescu, and then he said that, well, QL has 5 degrees of freedom, Q star has only 2 degrees of freedom. Okay. Even though Q star approximates this one, the difference between the two should be captured in basically the difference, what is in the transverse direction. Right. So then I asked him whether he can do something about the difference of these things, and then we start our discussion, and then after some while we prove this one. So first of all, that the minimizer actually converge in a much stronger than uniform, right? As you want, to the minimizer away from the singularity. Now, the second part here is basically what I want to discuss further, is that assume that Q star here has no singularity at all. Then you can actually show that the conversion from QL to Q star is of order L, okay? And then it has a profile. Right? You factor out, you have a profile. Now, this profile, can you determine it? The answer is yes. So if you split this Q dot as A plus B, where A sitting in a normal space to your limit manifold, and B is tangential to the limit manifold, then the normal component is determined from Q star by this algebraic relation. It looks horrible, but it's completely determined. And now this B here, the tangential component is determined by solving a linear, non-homogeneous elliptic equation. system. Right? So only this is the source. The rest of this one is just something in B, right? Linear in B. And this is some kind of a bracket product I don't want to write down. But there's this source, and the source is already determined from this one. So that means that if we know what Q star is, we completely determine this Q dot. And then if we can compute this Q dot here, then we are going to be able to say something. So in principle, this part here should be true. This part here should still be true if we have a singular point. The part that we don't know if it is true is whether one can say something like this, whether you can prove that there's a limit if Q star has a singularity. And so this is what is missing in our understanding how to go from Q star to construct line defects and point defects. Line defects and wall defects. Okay. So then, okay, before moving on, let me just give you some rough key idea in the argument. Is that as before in the Gimbel's-Landau case, one can actually show that you only need to look into the transverse direction. And somehow the equation of tangential direction is not that important. So maybe let me draw it. So this is the space of so this is the space of symmetric traceless matrices, and this one here I have a projective sphere somehow. So this has dimension 2, and now at every point here I can look at the tangent space and the normal space. So this is the normal space, and this is the tangent space. So what I'm saying is that we don't have to look into the tangent space. As long as you control the behavior in the normal space, you're happy. Now, there's this tensorial quantity that I wrote here. So this one here is exactly the minimal polynomial for the limit manifold. So this polynomial here vanishes everywhere on the limit manifold, and wherever this vanishes, it has to be on the limit manifold. Okay. So that means that this measures how far you are away from the limit manifold. Okay. So somehow this is our replacement of the modulus in the Gimbel's-Landau theory. And then we can show that this one here has order L, and then we factor out this guy x. Okay. Now we need to bound this x to go further. Then here is the point that we need to do some Lie-Algebra decomposition of this one, and this is somewhat nice. So let me explain it a little bit. So let's say that we are at a point Q on the limit manifold. Then this normal space here consists of all matrix M that commute with Q. Okay, so that's a characterization of the normal space. So now, so in particular, Q is in this normal space. Okay, and furthermore, what we see is that if M is a vector in the normal space, then Qm is also in this vector space. Right? So in particular, Q acts by left multiplication on this vector space. Okay, so I can think of Q as an operator on this 3-dimension submanifold, and then I can look for the eigenvalue of this one and the eigenspace of this one, and then we can do the eigenspace decomposition of that. Then there is a double eigenvalue and a simple eigenvalue. So the key observation in our work is to recognize that to control this x, you don't need to control all 3 directions. You only need to control 2 directions in this double eigenspace. Okay, so the other one can be controlled by some algebra, basically just the Cayley equation. Right? It says that if you have a matrix, then this matrix would annihilate the characteristic polynomial. That's it. Okay, so this missing direction is being controlled by that. Okay, so you only need to this one. So we reduce the 3 unknown into 2 unknown, and also at the same time we observe that this new system enjoy a maximum principle. So we recover maximum principle, which is missing from before, and this is the key point for our analysis.
For what? For each component or
for the whole matrix. Yeah. Right. Right. It's only as a matrix that we see that for each of the. It is very difficult to distinguish the 2 directions in this one because they have this rotational invariance. So it's a kind of. It might be true that might be true that there is a special way of distinguishing two special directions, and then you would have that, but that seems difficult. We didn't study. Okay. Okay, so let's go back to the other question, is that we want to study what happened to the QL near the singularity of the limit minimizer. So now for Q star, then it would look like just the standard hedgehog, like this one, right? So in terms of the vector n look like x over mod x. So that's the hedgehog for us. So then the Q tensor would look like this one. And then what QL look like is still a mystery, because here there's a competing issue between radial symmetry and axial symmetry. And physics seems to say that it would prefer axial symmetry, but of course as a PDE analyst, one would see that we have full symmetry is the most beautiful case, and it turned out not to be the case. So we don't know what to do here yet, so then we go on to try to study this before we say anything further. So let me now move on to the second part of the talk, just to study radial symmetry, solution with radial symmetry now. Okay. Now, so we define that a Q tensor is radially symmetric if the value at a rotation of a point x differ from the value of the tensor as the point x by a conjugation, by the rotation. And then there's a simple lemma that if Q is measurable and radially symmetric, then you can write Q as a scalar factor multiplied by the hedgehog. And then this one here is depend only on the radial variable. And okay, and now from now we can write out the equation. Is that again, as we said before, that instead of fixing the domain and let L go to 0, we can alternatively fix L equal to 1 and let the domain go to the entire space. Then the equation for Q is in the entire space now, Laplacian of Q equal to this polynomial in Q, and this guy here is the Lagrange multiplier that takes care of the tracelessness constraint. Now, the fact that that we have before, that Q converges to Q star in when we stay far away from the core, translate into Q equal to this S plus multiplied by the hedgehog for last radius. Okay. So now we would like to look for a solution of this one, and in particular now we only look for a radially symmetric solution of this one to see what we can say about that guy. So then we use the previous lemma, then we reduce our equation into u double prime plus 2 over r u prime minus 6 over r square u is equal to this cubic polynomial, and at infinity u is going to be S plus. At 0 before here there's no condition on Q at the origin, but now we have to enforce this because of this form, right? So Q is equal to U multiplied by this guy here, but this guy is singular at the origin, right? It's discontinuous at the origin. Whereas if we have a solution for this PDE, then it doesn't see what the origin is. So at the origin it has to be regular, so that means that U has to be 0 there. That's just an artifact of that specific, and it's good to observe that this constant S plus here is exactly the place where this is equal to 0. So let me draw this function. The graph of function f looks something like this. So this is 0, this is S plus, and there's an S minus which has smaller magnitude, and then it looks something like this. So it's a cubic polynomial. This is f of 1. Okay. So this is what we proved. Probably if you were in a satellite meeting some while ago, you probably have seen it. Is that so? We proved that there exists uniquely an entire radial solution. Okay, and this the radial profile of it is positive away from the origin and strictly increasing. And this solution here, which we call the melting hedgehog because it has an isotropic melting point at the origin, this one here is stable at low reduced temperature. That means stable for a small constant A, and unstable at large constant A. Okay. So this second part here is not new. This second part here was proved much earlier by Garland and Markner, and we just formalize it in a different way. And the stability statement here is new and much more challenging. So our contribution is basically the uniqueness here and also the stability statement here. So this has been reported some while ago in Oxford, so by Slastikov. So I skipped that. I just now focus on these.
What do you mean stability? Hessian?
The Hessian is strictly positive. So here we're strictly positive. We have to be careful a little bit because there's a kernel, right? Because so we show that the kernel is generated exactly by translation of the solution. Okay. So now for existence, so basically we have a variational principle. So we reduce it to that this particular case. We get this one here, and then you can show that this one energy here, the Euler-Lagrange equation of this energy here, give you exactly this equation. Right. So now H is the antiderivative of capital F. So the strategy to do this is that we start with a finite interval from 0 to some finite r, and then we minimize this one here. We obtain a minimizer, and then somehow we let the radius of r go into infinity. Okay. So for finite interval, we prove existence of a non-negative minimizer. This is rather easy, straightforward, just calculus variation, nothing. Now the key point is that we want to let the radius enlarge, and then we want it to stabilize to some profile. We don't want that it shrink down to 0 or it goes somewhere in between. Okay. So now here there's two things to rule this out. First is that we have to rule out the fact that it doesn't flatten to 0. We do this by saying that it has a minimizing property, and to say that if it leaves 0, then it has to go all the way to S plus. That's the monotonicity property. Okay. So I'll talk about the monotonicity here is somehow intricately related to the uniqueness, so I'll talk about that later. For now, let me try to convince you that the 0 solution is not locally minimizing, and so it would not be a limit of something like this. Okay. So now we want to say that 0 is not locally minimizing, so that means that we have to produce a function phi that has compact support, and somehow the energy of phi is smaller than the energy of 0. Okay. So now, if we look into this one here, this guy is positive, this guy is positive, so the only chance that we can win is from this term. Okay. So now this function x is the antiderivative of f. So if we want this to be negative, then we better stay in the regime where f is negative, which is precisely from 0 to s plus. So this upper bar is s plus. So I put up a bump here. And also that the larger the support of phi, that means that the longer the inner go here, it would be better. Okay. So what we do is that we start with an arbitrary phi. We just translate it, make it the support twice larger. So phi 2 of r is equal to phi of r over 2, and then we make move all the way down. Then just as algebra. Then now very simple. We see that e of phi n for n large enough would be smaller than 0, and then we're happy. Okay, so now we come to uniqueness. So uniqueness is related to a comparison principle. Right? So basically we want to ask this a little bit more generalized question, is that if I have a super solution would mean that I have the left-hand side, right, this linear operator is smaller than this one, and a sub-solution would mean the reverse inequality. Okay? So if I have U1 is a super solution and U2 is a sub-solution, and I assume that they both satisfy the same boundary condition, now the question is whether we can say U1 is bigger or equal to U2. Okay. The answer turns out to be no. Okay. This is wrong. So just shred it. However, something along this line can be proved under more restrictive hypothesis. So let me go now to the Gimbus-Landau case, where the case we know a lot about. So there's been some work here. There are more, but these are the key development in the study of this for the ODE. So the key feature in all of these studies is that the potential f of u is now minus u plus u cubed. So there's no quadratic term. Okay. So then the key feature is that the function f of u over u would be increasing for u positive. Okay. And now a consequence of this is that the answers to this one would be yes if both of them are positive. Okay. So now how do we prove it? Let's say that u1 and u2 are two positive solutions, then we look into the ratio of the two solutions. Okay? So now the ratio of the two solutions will satisfy this linear equation. This is just a computation. Now assume that we are looking at a maximum point of W. Okay? So at a maximum point, this is 0. This one is negative. That means that this guy here has to be negative. W is positive, so that this has to be negative. Now Fu over U is increasing. So if this is negative, then we must have U1 is smaller than U2. Right? But that is the same as W is smaller than 1. So at a maximum point, we must have W is less than 1. That means that W has to be less than 1 everywhere. And now by the same argument, we can say that the minimum is bigger than 1. So that means that W has to be 1 everywhere. Okay? So if W is 1, that means that U1 and U2 are the same. So here I have the argument for two solutions. You can do this for super and sub solution. Nothing changed. Okay. Very good. So now in our case, the f of U is minus a squared U minus b squared over 3 U squared plus c squared U over 3 U cubed. Okay. Okay. So in the Gibbs-Landau case, this term is not there, then it's okay. Now in our case, it's very important that we have a minus sign here. If this was a positive sign, then we can apply this same argument, everything go through. The key in our thing is that this guy here come with a negative sign, and actually it's a coincidence which is very nice, is that the sign of this one and this one here always coincide. Okay. There's another case that we didn't consider, is that when this one here is positive, that means that you go below the isotropic temperature or something. And I don't know much about that case, only that the only thing that I know is that some maximum principle fail in that case. Maybe that's more interesting. But anyway, so in this case here, we already see a failure of this argument. So this condition is sometimes called the Krasnostarsky condition for uniqueness. There's also another, right, so let me go back to the equation. So the equation is this equation. There's also another condition that also guarantees a comparison principle, is that if the function f is increasing in U. It's not just f of U over U, but the function f alone is increasing in U. And of course, that's not true in this case. So we also not in that case. Okay. Now, then we need to look for more for a stronger maximum principle, and it turned out that we can prove in a more general setting, so that if we just want a comparison principle, what we only need is that the function f has two zeros, one at 0, one at s plus, and it change sign from negative to positive across s plus. And I purposely make it here, it looks not clear whether it is tangential or not tangential, and it is like that. Okay. So either case is okay. You don't need any assumption here. The only assumption that you need is that there's a strength when it exits this one. Okay. So under that, then assume that f satisfies all of those, and you have a super solution and a sub solution. Now, if the super solution is non-negative, and then if they behave nicely at infinity, so this is a technical part that we need to enforce. It looks very simple, but I need to explain a little about the asymptotic, and I don't think I should do that, so let me just leave it like that. Okay, so the key point is that if the super solution is positive, then the super solution dominates the sub solution. Okay, so this proposition here proves that the positive solution is unique. So if we have a positive solution, then it's unique. Okay, so let me try to give some key ideas. So the idea of the proof is by this sliding method of Berestukey and Nirenberg. Okay. So the observation is that if U1 is a super solution, right? So assume that the blue curve here is the super solution, and the black curve is a sub solution, and for some reason the blue curve is not above the black curve. Right? So this is the picture we want to rule out. Okay. The observation is that now we start with this U1, we form this scaling, okay, and U1CR is equal to U1 of CR when C is positive. Okay. Then U1C is also a super solution. So now let's see what happens. So for some c bigger than 1, but still very close to 1, we move it a little bit to the left. So we call it slide it to the left. Now, okay, when we begin to move this blue curve is not above the black curve yet. Okay. Now, if we move it all the way here, then this gets closer and closer to S plus on top here. So that means that at some point we must be strictly bigger than the black curve. Okay, so at that point I call it the stopping time. Okay. Now let's look at the stopping time. Okay. So at the stopping time, what happened is that now if we try to reverse the process, then as soon as we slide this to the right, we would be below the black curve at some point. Okay. So that means that 3 pictures can happen. Is either we must have a place where the two touch here in between, or something at the origin and something at infinity. Okay. So so now what happened here is that because of the ODE, the behavior here has to be quadratic. Okay. So the first order term has to be quadratic. So that means that if you cannot move it, then the second derivative has to agree. Right, move to the left. And something likewise happened at infinity. So that's more ugly to write down. So let me just write this up there. So now, this first case here can be ruled out rather quickly by just standard strong maximum principle. Right? So here you are at a point where the equation is non-singular. You have a super solution, you have a sub-solution. If it touches a point, it has to be identical everywhere. So that means that this curve here, the blue curve, has to be identical to the black curve. That means that the original blue curve is somewhere down here, which is not right. Okay. Now, at this point here, if the leading order term was linear instead of quadratic, right? So this is the equation about the gradient being equal. Right? So now we know that if this was a regular point, we know that if the gradient cannot equal because of Hopf lemma. Right? So if we have a super solution that is larger than the sub solution, then they have to separate with a strength. Right? So here we have to prove a degenerate Hopf lemma, because here we know that the leading term is quadratic, so we have to do a degenerate Hopf lemma, and we just prove it. So this case is ruled out with some Musso. Now, the case at infinity is the funniest of all of these. We cannot rule it out. Okay, and it seems like that there is a case where you can actually have this sticking business at infinity. And so in ODE analysis, some people call this Jeffrey ODE with Jeffrey behavior at infinity. And then, so what we do is that we just make an assumption to rule it out. And the assumption can be checked particular for our equation. Okay. So that comes into the assumption of the theorem is that something about behavior at infinity. So you have to do it with some assumption, otherwise wrong. So we rule it out by fear. Okay. So that means that the original picture here cannot be the case. So which means that we must have an ordering like this. Right? So the blue curve has to be above the black curve. And then that proves the comparison principle. Okay. So this proves that this finishes the proof of the comparison principle, and also proves that the solution, if it is positive, has to be unique. Right. Now, we haven't finished the proof of existence yet, right? Because remember that the proof of existence, we need to show that it doesn't, if it leaves 0, it has to go all the way to S plus. And that relies on the fact that its U is increasing. So how do we prove it? Okay, so we start with the solution U. Then we say that this has to be increasing. Why is it? Because we start sliding it to the left. We would get a super solution. Then the super solution dominates the solution. And if we just write out, this is precisely the fact that U is monotone. Okay, doesn't matter how small you slide. As soon as you slide a little bit, it becomes larger. So that's monotonicity, and that also proves uniqueness now. Okay. Now, at this point here, I would like to talk a little bit about non-uniqueness. I think I go too fast. Okay. Right, so we prove that the existence of a positive solution, and we also prove that that solution is unique within the class of positive solution. So now the question, does there exist a sign-changing solution? Okay. So that has to come with a cost. Okay. So now, if we just consider a nonlinearity of this form, not of the form that we're looking here, but some form that look like this. So on the negative, for negative t, f is positive, and somehow it become growing here. And then let's assume that for simplicity that the growing here is like something like fourth order instead of cubic here, right? Fourth order. And then satisfy some behavior here. Then in this case here, on top of the positive solution that we proved, which is a minimizer, there's also a mountain pass solution. Okay. So now there's this mountain pass solution, and then now because of the uniqueness of positive solution, this mountain pass solution has to be sign changing. Right? Cannot be positive. So there exists a sign changing solution. So that means that to prove uniqueness, we need to enforce some stronger condition on this one. Right? So this is a proposition that we prove. Okay, we have to come back to some condition that look more like closer to this form. So the condition that I put here is satisfied by this particular nonlinearity. And under this condition, then any solution has to be positive. And so by the previous lemma, it has to be unique. Okay. So let me try to explain a little bit how this analysis come about. Okay, this condition come about. So this is S plus, and let's say that we have some solution like this one. So this is your solution U, and we want to rule out a picture like this one. So this is R and this is U. So the argument that we do is that first of all we are going to look into the logarithmic scale. So T is now going to be log of R now. Okay, and this is still the U direction. This is S plus. Now we look into the last lobe here, the last negative lobe here. It will be something like this in this picture, and then it continues somewhere to S plus. Okay, so now there's no color chalk now. Okay, so what we are going to do is that we are going to take this piece here. We do a reflection about this point. We obtain a curve. Okay, so this curve here is the reflection of that. Okay, so now this function here satisfies some differential equation because this satisfies a differential equation. We just write out what it satisfies. Now you can check that at this point here, this dash curve and then the solid curve agree up to the up to the third order, and at the fourth order it's separate. And then you can see that the dash curve has to go above the black curve. The solid curve for some y. And at some point it has to cross because the solid curve would go all the way to S plus, and then the dash curves go back to 0 because of this point. Okay. So now, then you have two functions satisfying two ODE, and you want somehow to compare it to prevent this picture from happening. Then you need to compare this point and this point here. Right? And this point here is coming from down here. Right? So this comes from a negative guy. So this there's some quantity that come into U1, and this is F minus U2 would come into this one because it comes from into this one here. So that's why there's this relation when we want to compare F of T1 to F of minus T2. Okay, so as long as we have a condition like this one, then the argument is going to go up. So maybe I have a
yeah. Okay, but concretely in your conditions you have some parameters A
yeah.
and so forth, and for what kind of parameters you have this property?
So this condition is satisfied for all A, B, and C.
Oh.
Yeah. So the picture that I showed you before, this picture here is for not cubic but quadric. Okay. Now I like to point out something which is a little bit interesting, and I still don't understand what's going on. Is the case of quintic singularity, nonlinearity. right? So remember that in at the beginning we were looking at this one here, right? Where I assume that this is a fourth order polynomial.
You are in 3 dimensions.
Yeah, in 3 dimensions. Okay. So now, if we look into instead of truncating the energy density as the fourth order, we can also look at FB, which we can look at into the 6th order. Right? This is also another one. The only difference is that in this case here, the Euler logarithm equation become critical in for the embedding. Yeah, and then there is some argument we need to do here. Now, what is interesting is that when we look for ODE solution, what we observe, so this is not proved rigorously, but only numeric so far, okay, is that for 6th order solution, what we can see is that there is this positive solution that we get, which is unique in the positive class. There is also another sign changing solution that looks like this one. Okay. So this one here is a little bit funny, right? Basically, because what we have is that at this one here, right? So remember that Q is equal to U multiplied by the hedgehog, right? So at this point here, Q is 0. Right? At this point, Q is 0, and at this point here, Q is also 0. So that means that we actually have a sphere of isotropic melting point. Okay. So furthermore, at this point here, the gradient of Q is 0 because U is second order here. U should be quadratic, like this. On the other hand, at this one here, Q is not 0. Okay. So basically, we have a sphere of isotropic melting point with non-vanishing gradient. And I don't understand what this means physically. Okay, so I would be interested in talking about that if you have some intuition in what happened in that case. Okay.
Okay. Have you checked if you just replace that dip in the quintessence with a straight line, so making isotropic all the ball inside the sphere, what happens to the energy? Does the energy increase or decrease?
No, I haven't checked that. Yeah. But I suspect that this one here is not stable. It has to be unstable, and maybe that's related to what you said. Yeah. Right. So the suspicion is that this is not going to be locally minimizing in any sense, and so I mean physics would prefer to state on the other state. Okay. So wow. Okay. So there's some open problem that I have. I mentioned at the beginning is that I want to prove the rate of conversion when I have singularity. So that's still a lot of work to do, and the profile near the core. Then that will be the next step after this. Right? After we study the radially symmetric solution, we show the instability for large temperature. That means that the energy minimizer is not radially symmetric in that case. Right? And then so we already have an indication that it would want to correct the radial symmetry to go to smaller energy. Now, but at low temperature, we actually prove that the radial hedgehog is stable, so locally stable. So then we don't know whether it is the global minimizer, and so that we need to come up with some other argument to rule out that it is not the global minimizer. Okay. So this is also related to this axial symmetry. And this existence of melting point is related to what I just described here. So, and again, I thank my collaborator, and thank you for your attention.
Time for more questions?
Yeah.
So after you've proven all of this, can you tell us what your preferred shape is and how big the core is?
How big the core is, I don't know yet. So that is part of.
But I mean, in terms of scaling, it has to be something like the coherence length of the QIJ tensor. Right?
Yeah.
So you should, I mean, just to be sure that we're the same rate. So the thing should sort of rise exponentially, and beyond that length, the U of x should be approximately flat.
Yes. So this is.
Getting that?
this is the profile that I was saying here. So this is, that's why I have been drawing something like this.
Of course, I look at that and I say, oh, you've spread it out a lot.
No. This is only a finite interval. What I mean is that on the infinite interval is almost S plus.
So the point there is something like the ratio of the gradient to
Yes.
Q squared term to
Yeah.
the rest.
Yeah.
I missed the beginning of the talk, but are the axial symmetric solutions, are those unstable when the temperature is low?
Well, the conjecture is that the actually symmetric solution is actually the global minimizer, and that has not been proved. And also, the existence of that solution has not been proved. All of this is conjecture numerically.
So what do you mean by actually symmetric? In other words, it has a cylindrical symmetry.
Yes.
And so other than putting a disclination ring in the middle to
Yeah,
replace
it's this biaxial torus that we want to look for.
So you think that you'll make the core biaxial before you get to disclination?
Yes. But all of that is very far. We have absolutely no intuition so far.
Presumably depends more on the relative magnitude of the different Planck constants.
And what's happening with the topological charge and boundary conditions? I mean, how are those?
Right. So that's a very good point. I have been trying to neglect that. That's actually okay. Then I should go back to the very beginning. Okay. So right. So we impose this energy thing, and then we are talking about minimizer. Then we have to impose some boundary condition. So for all of these talks, so what I have been assuming is that I assume that Q restrict to the boundary of omega is actually taking the value from out into this limit manifold ready. Okay. So ready. So basically, on the boundary, I assume that it is uniaxial. Okay. So now one can also ask the question. Okay. Well, there's nothing wrong with this. We do this, but there's also nothing wrong with assuming that it's take value into the larger class. And what is going to happen? Now, if we are going to do that, then right. So Q would prefer to stay on the limit manifold, but at the boundary, if you impose that it's not on the bound, on this limit manifold, then something has to happen. And then we suspect that some kind of boundary layer would form, and then but that would be very difficult to study at this stage. Because then one have to see how large is this layer, and then there's some numerics on that, though, I think. But from the analysis, I don't think anybody has looked at that.
Other questions? Okay, let's thank our speaker again.